We're going to take a look at the end behavior for polynomials in this video. So we're going to just do an investigation to see if we can look at some patterns and come up with some generalizations of how the ends of a polynomial look depending on a couple of different things: the degree of the polynomial and the lead coefficient of the polynomial. So those are two things that I really want you to be paying attention to. What is the degree, what is the lead coefficient, and how does it affect the end behavior? All right, so we're going to just do some, you're going to need a graphing calculator eventually, but for this first part, we should be able to do this without a graphing calculator. We're going to graph a couple of linear functions. And notice there are no units on the XY axes here. So we're just going to get like a general idea of what the graph looks like. So this first function right here, y equals 3x plus 2, is linear. Linear functions are going to be degree 1. So degree 1 polynomial called linear. And that's because the highest exponent you see there on the x is a 1. All right, so the degree is 1. The lead coefficient is 3. These are the main things you want to pay attention to. And before I can tell you the number of zeros, let's graph this. So linear functions can be graphed pretty easily if they're in the form y equals mx plus b. Remember that b is the y-intercept, so 2 is our y-intercept. And then our slope, m, is 3, which means that you're going to go, the rise is 3 and over 1, up 3 over 1. So we're just kind of estimating where that would be, about right here. Or if I went down 3, I'd have to go to the left one. That's a negative over a negative, which makes it a positive slope. And draw a line in there. How many zeros do you see? Zeros are your x-intercepts. How many x-intercepts, I should say, do we see? We see one x-intercept, 1, 0. And number of twists and turns. Well, a linear function is a straight line. There are 0 twists and turns for the linear function. And then now, this is the whole key to what we're trying to figure out, the end behavior. Meaning, as x gets really, really big, going towards infinity, so as x approaches infinity, we can never get there, so we're approaching it. So think of really big x coordinates. What's happening to y? And for all of these in this entire investigation, it's either going to be going off to positive infinity or negative infinity. So for this one, if I look at this graph, the bigger the x coordinate, the higher up the y coordinates are going. So they're going to positive infinity as x goes to positive infinity. So infinity, turn a paper to the side and make an 8 if you're having trouble with that. All right, and then on the reverse side, as x goes to negative infinity, what do you notice about the y coordinates? So as x goes this direction, the y coordinates are going farther and farther downward, and they're going to go towards negative infinity. So what f of x, remember, is the y values. They're heading to negative infinity as x heads to negative infinity. All right, so let's do this, this next graph here. You guys should try to graph that on your own. Again, we can fill this part in before we even graph it. The degree is 1. Exponent on the x is 1. The lead coefficient is a negative 6. So we have the same degree for both of these, but the lead coefficient for the first one is 3. The lead coefficient for this is a negative 6. So, graphing that, we have a y-intercept of 1 and a slope of negative 6. So I'm going to go down roughly 6 units and to the right 1 unit. Or if I go up 6 units, I'd go to the left. You have to either go down and right or up and left to make that a negative slope. And we get a graph that looks about like that. Okay, we still have one x-intercept, 1, 0, 1 real 0, and the number of twists and turns, again, it's linear, so that is also going to be 0. And then the end behavior, what's happening to y as x gets bigger? So as x is going to the right, what's going on with y? Is it going up or is it going down? And as you notice, as you get bigger values of x, this is going down farther and farther towards negative infinity. So that flip-flopped this time. So think about why you think it might have flipped. And then on the other side, as x goes towards negative infinity, what's happening to the y values? They are going up and up and up forever. So they are going towards positive infinity as x gets farther and farther in the negative direction. Okay, so one little thing I want to show you, and this is something you'll be using if you go into pre-calculus, instead of writing our end behavior like this, you can use something called limit notation. Limit notation is commonly used we'll be using it later on in this year. If you write it in limit notation now, I will give you extra credit for this assignment. What you do to write it in limit notation is, I'm going to take, here, let me color code this. I'm going to rewrite this in limit notation. So f of x goes to infinity as x goes to infinity. That means the x and the y are both going to positive infinity. So we write lim, stands for limit, of f of x, the limit of f of x, the highest it goes, the highest the y coordinates go as x approaches infinity. And that little x approaches infinity, that arrow means it's going towards infinity, and it's right underneath the lim, the word lim, and it's tiny. The rest of it is all the same size. What's happening to the y values as x goes to infinity? Well, the answer would be infinity. And then if I take this guy and rewrite it in limit notation, we know that the y values are going to negative infinity as x is also going to negative infinity. So we write lim, the limit of f of x is how you would read this, as x approaches negative infinity equals negative infinity. Okay, so you guys should try to write the other end behavior over here in limit notation and then check your work. Okay, so this top part, limit of f of x as x approaches infinity is equal to negative infinity, corresponds with this. And then the bottom one, in dark purple here, this one right here, the limit of f of x as x approaches negative infinity equals infinity is corresponding with that statement right there. Okay, we're going to pick up with the next function, which is a quadratic function, in the next video.